Recording is rolling. It is Friday, May 3rd. I gave you guys a study guide. So we're going to start going over this. It'll take us a few days. So the structure of your final exam is going to be the same as the midterm. If you remember that, it was in two halves. So same thing for the final. This is going to be 50 conceptual questions. Same ones as on your study guide. There's going to be 1 point each. And then there are 10 puzzle questions, 5 points apiece. So it'll be half and half, right? On your final exam, you can use your study guide, then calculator. So going over the questions. So I want to take some notes. There you go. Oh, seniors are going to take this final exam on Thursday, the 16th, and then everybody else is going to take it the week after. So it's going to go period 7, 6, 5, 4, 3, 2, and 1. Right? You guys got that? Right. Then in preparation for next week, of course, today we're on a Friday schedule. That's not the schedule, right? But on Monday, we're going to be on the schedule, and Tuesday, and Wednesday, and Thursday. So the schedule, we're going to see for a while. Guys, what's your very first class coming in on Monday? Period 2. And then you're going to have lunch with your fourth period, right? That's all on Monday, right?
Wait, next week is not, is next week exams?
There's all kind of testing going on.
Okay,
yeah, we are definitely in testing season. I know AP exams start next week, I think, right? Okay. Yeah. All right. Okay. All right. So you guys good on that front. All right, here we go. So I have 100 questions here. 50 of these are going to show up on your final exam. These are approximately in the order that we studied them, but I put the relativity questions first. So knock out this first. Okay. Question number 1. Light is different from objects with mass in that no matter how fast the source of light is moving, light always has the same what? Speed. Yeah, same speed. Right? So if you are grounded on a planet and you measure a light beam going by, you'll measure the speed of light as being the speed of light. If you're in a rocket ship going half the speed of light and you measure a light beam, is it still measured at the speed of light? Yep, sure is. Right. Now remember, that's different from classic Newtonian mechanics. So like if you're in the back of a flatbed truck and you're throwing a baseball back and forth, well, different observers might observe different speeds for the baseball. Right? But light, always the same. Remember, what makes that consistent is time dilations, length contractions. Okay. So question number 2, Einstein reasoned that, let's check this out. All motion is relative. Hence relativity. I think that sounds true. A spaceship cannot measure its speed relative to empty space. Also true. A spaceship can only measure its speed relative to other objects. True. Yeah, all the above. I think all the above on that one. Question number 3. A spaceship moves away from a space station at half the speed of light. If a person in the space station flashes a light beacon, people in the ship will see the light traveling toward them at a speed of. Guys, this question can only ever have one answer. Speed of light. There you go. Right? Speed of light. Right. And that's different from throwing a baseball at. Are you in the truck or outside the truck? You'll measure the speed. Right. Yeah, light's always the speed of light, no matter how fast you're moving. Suppose we observe light bouncing back and forth between 2 vertical clock mirrors in a spaceship whizzing past us at a very high speed, say a relativistic speed. Compared to what the person in a spaceship sees, we see the clock as running what? So this is, I made a poster version of this that I put them on a train, spaceship, same idea. Right? And then you guys remember we did Pythagorean theorem, and you can derive what is time for, I'll call it Earth twin. This is the twin paradox, isn't it? So what is Earth twin times in terms of rocket twin's time? T rocket twin. What you do is you take rocket twin's time, divide by this Lorentz factor, and this falls out of Pythagorean theorem. 1 minus v squared over c squared. That's the Lorentz factor. Right, guys, about right, so let's see, c is the speed of light. That's a universal constant. V is how fast is the spaceship moving in this case. Right. So let's see. Say rocket twin's been flying around for 1 year. Right, 1 year rocket twin's been flying around. Right. Now Earth twin is going to experience a different passage of time. Maybe you remember how this twin paradox works out, or maybe not. But if you don't, that's okay, because if you know this formula and you know how to read the music of this formula, then you can get to the correct answer anyway. Okay? So let's do this. Let's say this v is a relativistic speed. So it's some significant proportion of the speed of light. This fraction right here, b squared over c squared, isn't that going to be bounded between 0 and 1? Because you can never quite get to the speed of light. So that fraction is bounded between 0 and 1, right? Because what's 1 minus anything between 0 and 1? Is that also between 0 and 1? If you take the square root of that, isn't that still bounded between 0 and 1? Right? So let's take the 1 year that Rocket Twin's flying around. Now, that's 1 year from Rocket Twin's point of view. That's if you're aboard Rocket Twin's rocket. Oh, it's been a year I've been flying around. Let's go back to Earth. Okay? And you divide by anything between 0 and 1. Let's say like 0.5, right? Because what is 1 divided by 0.5? 2. So you go to talk to Earth Twin. Earth Twin said, you've been flying around for 2 years. And then now there's the mismatch. That's the twin paradox. So Rocket Twin says 1 year. Earth Twin said, no, it's been 2 years. Do you guys remember which twin got old? Was Earth Twin. And Rocket Twin stayed young, right? So different passages of time to experience. So back here, right? So now this question, Earth Twin is looking through a telescope through Rocket Twin's window in his rocket, right? And he sees Rocket Twin's clock is running how? Slow, right? Because every 2 seconds on Earth is now only 1 second of spaceship. So the spaceship clock, again, from Earth Twin's perspective, looking through a telescope, looks like this. Click. Right. That's the second hand, right? Now, of course, if you're on board the rocket, you don't notice anything weird. 1 second, so 1 second aboard the rocket. Okay, you guys remember that? Number 5, to calculate how much rest energy an object contains, you multiply. They're talking about nuclear energy here. You guys remember E equals mc squared? Right. So what does this mean? Guys, what does the E stand for? Energy. So how much nuclear energy we're getting? What does the M stand for? Mass, like a mass change, right? And then what does the C stand for? Speed of light, right? So really, this is a mass difference. So if you have, let's say, some uranium, like U-235, run that through a nuclear reaction, the mass will decrease, and that's going to convert to energy, and that's the energy on the electric grid from a nuclear plant. So it's the mass change times the speed of light squared. Okay. And that's the answer to this question. Right? How much rest energy we're talking about? Mass times the speed of light squared. Right? The idea of, well, okay, right. Rest energy is, there's a little bit more to that equation. If it's in motion, it's a little bit different, but yeah. If Einstein's equations of special relativity are valid, for example, this one right here is one of his equations, right? They must what? Let's say reduce to Newton's equations when the speed is small, give correct answers for speeds much less than the speed of light, agree with correct results of Newton's equations. Do you guys think all of those would be true? All the above is true, right? Yeah, so I'm gonna go with all the above. The term for that is called the correspondence principle. If you come up with some new theory about how something's supposed to work, it should agree with correct predictions from the old theory, but also predict new things that the old theory couldn't. And Einstein's equations do all that, right? Like here, if you look here, what if the spaceship was moving at a non-relativistic speed? By the way, even if you are in the International Space Station flying around the Earth every 90 minutes, that speed is tiny, tiny compared to the speed of light, which means that this ratio right here, b squared on c squared, is approximately what? 0, right? B is much, much, much less than c. Guys, what's 1 minus 0? 1. What's the square root of 1? 1. And then, and then the guy based on Earth and the guy in the International Space Station agree how much time has passed, right? Now, Newton's physics made really accurate predictions correctly for hundreds of years. And then there were some fringe cases, like, I don't know, the orbit of Mercury doesn't quite line up, right? There were some fringe cases where it didn't quite work, but most of the time it did. Then Einstein comes along with some new equations, and those new equations not only align with Newton's mechanics at low speeds, but they're able to make predictions that Newton couldn't. Hence, we're allowed to use GPS and that kind of thing. Number 7, nearly all the elements heavier than hydrogen that occur today were created. I think I mentioned this one in passing. Let's go with deep interior of stars. Right? So nova and supernova explosions. So Big Bang happens, and for about the first million years or so of the universe, there was mostly a bunch of hydrogen and maybe some helium. Okay. So where did we get like all the carbon and oxygen, and where did all that come from? So in our own solar system, there was probably some nova explosion that happened about 4.5 billion years ago, and that's where we get everything that we have on Earth from there. Right? Otherwise, it'd just be mostly hydrogen. All right, so we're done with the relativity. Moving on to materials and thermo type questions. Which has more density, a loaf of bread just after it comes out of the oven, or the same loaf squeezed into a small volume? So density, here's density. Is that mass per unit volume? Right. So that's some intrinsic material property. So here we're comparing the same mass of bread, but different volumes. So guys, if you have a smaller volume, is that therefore a larger density? Right? Right. You take the loaf of bread out of the oven, throw it in a lake, it'll probably float. But squeeze it down to like a tight little bread ball, and more likely to sink. Right? A block of iron heated in a furnace, where it consequently expands. Right? You guys remember thermal expansion? Right? And the expanded condition, its density is, here, you can do this one again. Yeah, it's the same mass, but in the expanded condition, now if we heat it up and expand, that's a greater volume. Is that a smaller density? Smaller density. Oh, yep.
And what was number 8 again?
Number 8. Okay, if you take the loaf of bread, right, fresh out of the oven, has some mass per unit volume. Right here, maybe we should all it up. Right. So here's loaf of bread. Right, it has some mass, some volume. Great. Now we're going to squeeze it down into a little tiny bread ball. So it's the same mass, but a smaller volume. Right. So if you have like 12 over 4, that's equal to 3. What if you have 12 over 2? Is that equal to 6? Right. So see how if it's a smaller volume, it's a larger density, right? Right. You guys got that? Right. Number 10. When used horizontally in construction, an I-beam is nearly as strong as a solid bar because, right? So here, say you're on a construction site one day and we're laying down some bars, right? We got the steel bar, and then we're gonna possibly encase that in concrete and move on, right? And someone says, hey, hang on a minute. You know what we could do? This steel is really expensive. What if instead of that whole steel bar, what if we carve out parts of the middle? So hence we're getting an I-beam. Now, this is realistically what you actually see in construction sites, right? The first one is just hypothetical, right? So now we got that shape, and then we embed that in concrete and all that, right? And this one is nearly as strong as this one, right? And it's probably less expensive too, right? So why would that be? Well, think about it this way. Suppose you put a huge force on the top, and it's got some supports down here. Does this kind of want to bend like a smiley face? You guys think kind of like that, right? Bend, right? But it has in the top is going to go into compression and the bottom is going to go into tension, right? But the stress is 0 right in the middle. There's some axis where there's 0 stress at all. And in fact, there's smaller stress overall in the middle. So you don't need as much material because there's not nearly as much stress in the middle. Most of the stress is in the top and bottom flanges. Isn't that true? Right? Let's see if there's an answer choice that basically says that. See, the I-beam weighs less. Probably not what we're looking for. It's perpendicular gravity. Effects of scaling. The tension and compression are predominantly in the top and bottom parts. There you go. So engineering there. Less force is required to poke through an eggshell from which side? Let's look at an eggshell. Right, here could be an eggshell. Right. There's a physics perspective on this. There's maybe also a biology perspective from this, right? So you got like a little chicken here, right? It's ready to break out. Right. You know what this goes hand in hand with is how about an arch bridge? You guys ever seen those like stone bridges? Could be like an arch shape, walk across the top. I bet there could be a lot of compressive strength in that stone or possibly concrete, a lot of compressive strength, right? Right. But guys, do you ever see a stone bridge that's like this? I mean, maybe those little floppity bridges, right? But made out of rope, but not a stone bridge. You wouldn't do that because like stone or concrete has hardly any tensile strength. Right? So this would break really easy. This is going to hold because it has huge compressive strength. Well, back to the egg then, right? Is it really easy for the little baby chick to get out? Probably so when he's ready to get out. Or is it really hard for predators to break in? Yeah, really hard because this eggshell has a lot of compressive strength, but not nearly as much tensile strength. Right? So I think it's easier to break out than it is to get in. Right? Right. So there's also maybe a evolutionary perspective you could back that up with too. Right? So less force to inside out than outside in. Less force to break out. Which geometric shape has the least surface area for a given volume? So suppose I give you a little lump of Play-Doh, and I say mold this into some shape, and we're going to paint it. And I want to minimize the amount of paint that it takes to cover the entire thing. Guys, what shape are you gonna roll that Play-Doh into? A sphere, exactly, a sphere, right? Do you guys happen to know, maybe some of you guys know, what branch of math could you use to prove that? Okay, yeah, actually, that is true. You got me there. Yeah, so geometry, your take, right? I'm thinking calculus. You guys, anytime you see least, most, you want to maximize or minimize something or optimize something, the branch of math you're going to go to is calculus, right? So if you're in calculus or if you take calculus one day, look for optimization. Oh, 13. Which will cool a glass of water faster, ice cubes or the same mass of ice crushed? Oh, 12? Right. Yeah, if you want to minimize a 3D shape, minimize the surface area for a 3D shape, you're going for a sphere. Right. Right. Kind of similar idea if you want to minimize the perimeter of a 2D shape. Do you guys know what has the smallest perimeter on a 2D shape? A circle. Yeah, circle. Right. If you have someone, or the other way to think of it is suppose you have some amount of fencing material. You know, say I want to maximize the amount of land that I can fence in with some limited fencing material, then you would also make a circle. Right? Which will cool glass of water faster? Ice cubes are the same mass of crushed ice. So, I mean, it's the same mass either way, right? Oh, but, guys, is rate of heat transfer proportional to the area? And guys, which has more surface area, the cube or the crushed ice? The crushed ice has more surface area exposed, which means there's going to be a faster heat exchange. In which, in this case, it'll cool down your glass faster. Okay, going for the crushed ice. Okay. These next two questions go hand in hand. We've got an elephant growing to twice its height. You guys see elephant twice the height for both 14 and 15, right? So number 14, the area of its ears would change by a factor of. So I have a poster for this scenario. Right? Got time to start with this little box in the bottom left. And now my poster version, I blew it up by a linear factor of 3, right? So twice as wide, twice as high, and twice as deep, right? And then there could be different questions you could have that are either linear, 2-dimensional, or 3-dimensional. Now this one is an area question, right? So let's do, here's the original, say like a front surface of that box. What if you blow it by a factor of 2? Right? Now I got twice as wide and twice as tall, because that's how many times the surface area? 4 times. So I'm going to take this base value 3 and change it to 2 for a linear factor 2. 2 squared is 4 times. So it'll be 4 times the area for the elephant ears. Right, is that true? Right. One of the reasons elephants have those big ears, they're such large animals, they need to radiate away a bunch of heat energy. So they need to increase the surface area, and large ears help them do that. Yeah, so true. And then, all right, so number 15, also growing twice as tall. Remember, if he's growing twice as tall, he's changing in all 3 dimensions. So now we have a 3-dimensional type question. Its weight will increase by a factor of. Let's see, weight is proportional to mass. Mass occupies volume. So you could replace this with its volume would increase by a factor of. All right, and guys, what is that? What is a factor of 2 in 3 dimensions? It would be 8, wouldn't it? Right? Because twice as tall, twice as wide, twice as deep. That's 2 to the power of 3, 2, 4, 8. That's 8 times. You guys got that? Now my poster shows a cube, but that could be any shape. An elephant's a weird shape, but that's okay. It's the same principle, same math, right? Guys, if you get a final exam that changes this to an elephant grows 3 times as high, could you guys also field that question? You guys could do that too, right? Right. Yeah. Same principle. Where is the pressure greater? 1 meter beneath surface of Lake Michigan or 1 meter beneath the surface of a swimming pond? I'm going to back up this with a physics formula. Right, let's drill a hole. All right, let's get a little lake or something going. Right, so here's some water. Right, got a lake, also lake, and let's throw some object in here. Right. Throw a little box in here. Maybe start falling to the bottom. Right. And I'm gonna label this depth as h. So h, like a height change, could be the depth. It's okay. Let's got that. Right. 2 formulas. So the pressure is equal to the density of water times the gravity field of the planet times how deep is this cube, right? And the buoyant force, this is called Archimedes principle, right, is density of water times the gravity field of the planet times the volume displaced, which if the entire object is submerged, then that would also be the volume of the object. Okay, you guys get that? Okay. So this question says, well, what if you have Lake Michigan versus like a little tiny swimming pool, and you're 1 meter down? Does the volume of the body of water make a difference? No. Right? So it should be the same, right? You're 1 meter down in water. It's the same either way. It's the same pressure. Archimedes' principle says that an object is buoyed up by a force equal to, that's why I just wrote you guys right here. Well, I should say this is the magnitude of the force. This is Archimedes' principle, right? Rho GV, right? Now, guys, what is density times volume? Multiplying these together. What is density times volume? Mass, right? And what is mass times gravity field? Weight, right? So what this also says is if you froze time and pulled this box out, and now there's a void, and you fill that void with water, and then you weigh that water, that is equivalent to the buoyant force that was pushing up the cube originally. That's Archimedes' principle, right? So an object is buoyed up by a force equal to the weight of fluid displaced. This way, we just walked through. The reason objects immersed in fluid experience an upward buoyant force. Yeah, why does the buoyant force push upward? Why isn't it that you jump in a swimming pool and it pushes you down to the bottom? Why does it help you float? Right? It's because the fluid pressure on the bottom of the object is greater than the fluid pressure on the top of the object. Is that true? Look at this. Right? I got this 3D object. The bottom part of the object is deeper than the top part of the object. That is a pressure differential, isn't it? I think that's a true statement. Yeah, true. Right? That's why the buoyant force pushes upward and helps you float in a swimming pool in the ocean. A hydraulic press works because, let's get a hydraulic press going. I do have a poster for this, but I'll recreate this here. Okay. Maybe one day you could go get your oil changed in your car. They put your car on a platform and start raising up. Right? That could be a hydraulic lift. It's the same idea as hydraulic press. So there's some input force here, and your car has a huge weight. Call it like F2. Right? Now the input area might be small and the output area might be large, right? Because the pressure, and this could be some hydraulic fluid here. I'm trying to hatch this in. This hydraulic fluid has the same pressure everywhere. Well, okay, maybe it's a tiny bit more the deeper you go. That aside, it's the same on the left as it is on the right. Okay? And pressure is force per unit area. So we got different forces. The input force and the weight of the car are different, but they're also sitting on different areas. So a small force on a small force on a small area could be equivalent to a large force on a large area. Right? You guys get that? That's called Pascal's principle. So check this out. We're here. Hydraulic press works because Pascal's principle is operating. Bing. Liquids transmit pressure in all directions. Bing. Liquids transmit pressure undiminished. Bing. One piston is larger than the other piston. Bing. Give you a mechanical advantage, right? Mechanical advantage. All of the above. I think all those are true statements. Suppose a stone weighs 8 newtons in the air, but in water it only weighs 5 newtons. And when they say weighs, I think they're not talking about gravitational force. They're talking about, suppose you have it tied to a string. So here's a stone, you tie it to a string, you got to hang it from a scale, and the scale reads like so many newtons, right? They told us 8 newtons, right? Let's put 8 newtons on the board, right? But then we're going to take the same stone, same string, same scale, right? And we're going to submerge it in water, right? And now the scale is only reading 3 newtons, right? You guys see that? Right? Well, if you look at a free body diagram on the stone, I think it still has basically the same 8 Newton gravitational force, right? But the string's only put up with 3 newtons. That's because there's also a what force acting on the stone? A buoyant force of how much? 5 newtons, right? You guys think? Right? That makes sense. So, yeah, there you go. That's the answer. Right? You guys can do it? No, no.
I think you have the numbers.
Here. Oh, did weighs only, oh, yeah, sorry, you're right there. Yeah, okay. Yeah, you're right. I did get these flipped. Right. So yeah, if the scale only reads 5 newtons, yeah, you're right. Right. Then 5 newtons is now the tension force. This could be F tension. So the buoyant force would, yeah, now be 3 newtons. Okay. Yeah, there you go. All right. Okay. If you squeeze a balloon to half its original size, the pressure inside, you guys remember ideal gas law? So PV equals MRT, draw a little balloon. Make it shiny balloon, right? So we got pressure, volume, the number of moles of gas inside, some constant R, and then T is absolute temperature. Because if you ever apply this formula, remember you have to use Kelvin scale for temperature because that's an absolute temperature, right? You have to scale it up or down by some proportion. Right? Now in this case, they're saying you squeeze the balloon to half its original size. That's a volume change, the pressure inside. So we're really focused on these two variables here. Let's assume constant temperature, which is probably approximately true anyway. So all the stuff on the right stays the same, right? So it's equal to something, right? So if you have half the volume, then what has to happen to pressure? It has to go up, specifically by a factor of 2, right? Because 2 times a half is the original amount. Right? So half the volume is going to be twice the pressure. There's like a fly flying around inside your balloon. Yeah, half the volume is twice the pressure. A balloon is buoyed up with a force equal to the, I think we're back to Archimedes' principle again, right? If you have a helium balloon, maybe it's even more obvious, right? You release the helium balloon, it flies up in the air, right? So I'm going to say this buoyant force is equivalent to the weight of the air displaced. Let's see, is that an option? A balloon is buoyed up with the force equal to the, there it is, the weight of the air it displaces. A 2-ton dirigible hovers in the air. The buoyant force acting on it. Let's get a 2-ton dirigible. So here's a big old blimp. Right, and we're down here. Right, watch out these windows right here. So let's do free body diagram on this blimp. Free body diagram time. I think this big old blimp has a weight equal to 2 tons and a buoyant force also equal to 2 tons, right? So it's just kind of hovering there, right? You guys think 2 tons, 2 tons? A 2-ton buoyant force. If you are standing on the moon and release a balloon filled with helium gas, the balloon will. Who thinks they know the answer to that one? Yeah, sink. It's gonna fall straight down. Right, I'll draw it up for you guys. Right. Say you have Earth versus the moon. Okay. And let's go helium balloon. So here's a helium balloon. Say here's like the same helium balloon. Right. Now on, how would do it on? Right. Right. So let's do a free body diagram. Now on Earth, I bet this helium balloon has some weight, right? But the buoyant force is going to be more than that. Hence, it's going to take off up into the sky, right? But on the moon, now the moon has some weight also, not as much, so it doesn't weigh as much, right? But guys, does the moon have an atmosphere? No. So can there be a buoyant force? No. So the balloon's just going to fall straight down. When a river narrows, the water in the river flows. This reminds me of conservation of flow. You guys remember, say if you have a pipe system. Now they're saying river at a poster with a pipe system, it's the same principle. Say you have a large pipe leading into a small pipe, right? But the flow rate's the same everywhere because water is basically not compressible. Right? So you guys think area 1, area 2, say speed 1, speed 2. You guys remember area times speed is the same everywhere for an incompressible fluid, right? That's called conservation of flow. You guys remember that? Okay. Right. So turn this into a river. When the river narrows, what happens to the speed? Goes up, right? Increases. The river flows faster. You guys got? $26. You blow across the top of a piece of paper, the paper will. Oh, let's do that right here. Oh. Is it getting vacuumed up? Right? Because you blow a stream of air across, Bernoulli principle, the pressure drops. Hence, it's going to get vacuumed up, isn't it? It's going to lift. Temperature is mostly related to, we kind of talked about this recently with Maxwell's demon. Because remember, hot tank, cold tank, what could make something hot or cold. What I'm going to be looking for is not the total energy of something, because you could double the amount of material that would double the total energy, but it doesn't necessarily double its temperature. Right? Looking for the average molecular kinetic energy. That's what we're looking for. The average molecular kinetic energy. How fast are the atoms vibrating on average? Average molecular kinetic energy. The kinetic energy theory of temperature. The reason an ocean's temperature does not vary much from season to season, and hey, we're in Florida, we're surrounded on three sides by lots of water. Isn't it true we get relatively mild summers? Like it might get maybe up to 100 degrees Fahrenheit at most, but you know, if you go out to Nevada, it'd be like 110 degrees regularly, right? And also our winters are also pretty mild, right? So we don't have a whole lot of fluctuation from summer to winter, from day to night either, right? Because we're surrounded by water. Because oceans, I should say water has a high specific heat capacity is what I'm looking for. It's really hard to change the temperature of water, right? Put water on the stove, the metal and the pot will heat up real fast, but the water takes a few minutes, right? It takes a long time to heat up water. It also takes a long time to cool down water, right? All right, water wants to hold on to its temperature. The largest extremes in temperature. So yeah, let's go back out to the desert in Nevada. Usually experience, say, large coastal cities, San Francisco, no. Near the ocean, no. Japan, no. Islands, no. All those options, A, B, D, and E, are surrounded by water. Middle of a continent. If you've ever been out to the Midwest in the States, you could have a crazy hot day and also a crazy cold night. It could go from like 90 degrees Fahrenheit to like 50 degrees Fahrenheit from day to night, or something like that. You have crazy temperature swings. Okay. The fact that desert sand is hot in the day and cold at night is evidence that sand has a low specific heat capacity. It's relatively easy to heat up and cool down sand. Okay, guys good there? Is that a good pause point, you guys think? Good pause point? Let's do that right there. We're gonna put period 3 right there. There we go.